Okay, let me first thank you for your interest and for the invitation to come to Kyoto. First time for me in Japan, and very interesting. And we have beautiful blossoms outside. Unfortunately, they're already going. You see inside on the trees for lots of blossoms. So the aim of these lectures is to give some kind of introduction into random dynamical systems. And as I wrote on the pamphlet, you don't need really any prerequisites. It means I will try to kind of be as elementary as I can and still tell you something interesting. Of course, it's helpful if you know something already to compare what I tell you about maybe other things that are more useful. Another thing is that the course that I give is not really standard course in the sense that I don't know really of any textbook that really teaches this material at a level where I'm teaching it. So there's some advanced books which go in all kinds of different directions. But there seems to be little of a overview of the kind of the interesting things what you can do with random dynamical systems. So maybe some of you are aware of books on dynamical systems, which are very popular and are good introductions, like maybe a book by Bldg, or other people where you can actually get to come to understanding of some mathematics by through elementary examples and get some kind of feel what the challenges are. And somehow, up to the present date, in random dynamical systems, such a book was not written, and that makes it a little bit inaccessible. So there are several strands towards randomness. So of course, we have dynamical systems. Dynamical system, I will mean something like solution of a differential equation, that we see in mechanics and all kind of things. And there's discrete versions of that where we just have simple evolution, and we have phenomena like chaos and other things. So maybe some people are aware of this field. That is, of course, also what Professor Kukuku works. But now randomness, the idea is that somehow we add some randomness in these equations. So we have some equations, some idea of motion given by some equations, but a part of the equations there will be stochastic process. There will be something in these equations which are not constant. So usually when we have our equations in physics or in engineering, they're just kind of fixed. And these equations will change. They will change as a function of time, but in a prescribed way, which is basically statistically known, but not known exactly how the change is. So you say, well, why would we be interested in that? Well, I said a lot of people interested in that in various areas of applications. So nowadays there's like big words like big data, complex systems, and typically this applies to using mathematics, for instance, in the life sciences. And a lot of people there believe that the equations we have from physics are maybe a bit too easy, that maybe there's not a Newton's equation for some biological process. But maybe they believe there's some basic principles. And then there's some unknown things, there's some complicated things. And one way of taking care of complicated things is maybe adding some noise in some equation. Now the problem is then if some scientists like that come to a mathematics department and say, like, look, I have some interesting model that has like noise and all kind of things, what can I do? Then actually they get very few answers. Because unfortunately there's not so much known. Of course we have people doing stochastic analysis and some other things, and then special branches of processes of probability, and they do special problems in this area. But the kind of problems that I think random dynamical systems are trying to achieve, which is like, take an ordinary differential equation and add some noise in some way to this equation, is a difficult problem. You have a mixture between probabilistic theories and some kind of nonlinear analysis. Of course, I'm definitely not the first to think about these kind of problems, and there have been at least a few decades of people working on this, but the field has not really come to a level where, say, for instance, deterministic dynamical systems are, where there's a huge community working on this thing. What I'd like to get across, and it's nice to see that the audience is relatively young, that there's very good opportunities to work in this area, because there's a mixture between kind of probability and dynamics, and I think it's a topic which definitely will grow, and hopefully you can play a part in it, and hopefully so do I. Okay, good. So what I'm trying to do in the first lecture today is in a very slow pace to just go through the some elementary example, which is an example of a random dynamical system, which is so easy that we can more or less compute everything by hand. And that's rare. Most of the time, we cannot really compute anything by hand, and we have to resort to kind of abstract theorems and so on. But I thought to get an idea of what the objects are, it's good to work with an example which is completely under control. Of course, it's not the most general example, but it illustrates, I think, most of the concepts. And these concepts, although they're elementary, they may be not so easy. So it takes usually a bit of time to get to understand these concepts. Okay, so after the first lecture, then the second lecture, the third lecture, what we'll do is we basically work with the same tools and just look at slightly different problems, which are a bit more complicated, and where we also cannot do things anymore calculated by hand. But we will try to use the same concepts and the same ideas, and then we use and to see how things extend and what kind of problems appear. But still, these examples in the first three lectures will be relatively elementary. The first one definitely the most elementary. Then in the fourth lecture, we will talk about a set-valued approach to some of these problems, or 5 of those problems. And then the fifth lectures will be a bit more outward-looking. I will actually try to discuss, in some sense, how random dynamical systems theory could help, or where maybe the open questions and challenges to address problems in complex systems and by applications, etc. Okay. Good. Yeah. I wanted to start with something a bit strange. Maybe you say it at the end, but I thought I should say it at the beginning. Make sure not to forget. First of all, when one works in an area like mathematics, it's not just you just do it all by yourself. At least it works not for me like that, and there's a lot of people involved. So when I thought about it in the last 10 years or so that I've been working on some aspects of these problems, appeared to me a long list of names, colleagues and students, and also funders that help you to do. And I think one of the interesting things that I found is that among all the people that I work with and the students, there's 10 nationalities. And I think it just illustrates that, you know, doing mathematics or doing research is a very international affair. So I'm also very happy to be here and to talk about it. It's not some insular thing that a few people sit in a room and do something. It is something where the ideas come from many different directions, from many different people, and many people make different types of contributions. So we have people that are more pure mathematicians, some people are more like physicists, and so on, all working together. So there's a long group of people that I realized one way or another have contributed to some of the ideas that I presented here. And I'd like to express my thanks to Poincaré, who is also in the audience here, who was really helpful to put this lecture together. Okay. So Barnsley's chaos game. So we're going to do a little example of random numerical systems, and it is Barnsley called it chaos game. It's about 3 decades ago. The game is as follows. We look at a map just from the interval to itself. So we have the interval 0, 1, map it to itself. And we have 2 maps. The first map is T0 of x. So T0 of x equals to 1/3 of x. That's a contraction. So we have an interval 0, 1. The T0 of x maps this interval to the interval 0, 1/3, because contracted by 1/3. And the second map is 1/3 of x plus 2/3. And what it does, it maps this interval into the interval 2/3 of 1. So both maps are very, very simple, especially the foot of x here. And so the question is like, what interesting thing can we do with this set of maps? Well, the proposal is to take some initial point in the interval 0, 1 and to apply the maps T0 and T1 in some kind of random way. Yeah, so I take a point, then I'm tossing a coin, and if it's heads, I do T0, if it's tails, I do T1. And I just keep doing it. So this is an example of a random motion, which is driven, has two aspects. It has an aspect that I'm tossing a coin. That gives me a 0-1 sequence, which is, say, probability half or 0, half or 1. And there's also some element of dynamics, because every time I have a 0, I do one type dynamics, and I have 1, I do another type dynamics. Okay, so the question is, what can we say about the trajectories of initial points of this game? That's the challenge. So I'm going to talk basically for 2 hours just about this challenge. It can't be much simpler than this. So I just have 2 maps, they're both linear, it's going to be very easy, and I just do it in a random way. So maybe some of you say, oh, I understand everything, so you can now leave. Nothing to tell. But it's important, actually the question, like, which question should we really ask? Because of course, this is a very vague question. In dynamical systems, people usually ask the question, what happens if I iterate a lot of times and do things converge to something or so? That's a typical dynamical systems question. Okay. So the first problem here is that my first observation is that the points keep jumping randomly between those intervals. Because every time, so I take any point x, doesn't matter what point I take. If it's t0, it goes to the left side. If it's t1, it goes to the right side. Yeah. So this keeps happening. It doesn't matter if I iterate, it just goes more to the left, more to the right. But every time I iterate next, it goes all the way to the right, all the way to the left. Because I apply t0, t1. So it's clear that in some kind of rather, well, unpredictable way, this point keeps jumping from left to right. At least unless I have all the time zeros or all the time ones. Because then it will just convert to one point on one side. So the question is like, well, that's easy to see. And then you say, well, so what do we then know about this point? Not so much maybe. Well, actually, despite the randomness of the trajectory, you can see that after any iteration, any initial condition ends up in a subset of the interval, which is quite specific. And because despite the fact that we iterate in a random way, there's still some pattern emerging about the possible position where we can come. So this is the first interval, and I call it t0, like on the slide. And after acting on the t0 or t1, I see that I can never appear in the middle. I can never get here. So I go here or here, and I call this union of these two intervals E1. Now if I do it one time more iteration, so I get that this whole interval can either go to the left or to the right. So that means it can go to some picture here, or there. I call this E2, etc. So even though I don't know where the point is, I know more and more that it's going to go to some subset of the interval. It cannot go anywhere, everywhere. There's only a certain admissible set of points that it can visit. And this set where it can land up has a length overall of 2 to the third to the power n. Because every time that I shrink, so here I have length 1. If I iterate one time, I know that I'm a subset of length 2/3, 1/3 here, 1/3 here. If I iterate one time more, I'm in a subset of length 2/3 times 2/3, which is here pieces of a 9. Yes, 4 9. Etc. etc. So this set of points where I can end up shrink is small, and it's a well-known set. It's still called Cantor set. The most canonical Cantor set that there is. So it's an uncountable set of points, zero back measure. So the zero volume, and it converges very rapidly, exponentially fast, because it just uniformly contracts to the factor 1/3. And so very quickly I condense on this set. Okay. So in some sense, you could say that the trajectory is attracted to some set. But we don't know exactly where the point is, because it's still true that even though I have this Cantor set in the bottom, which is some kind of like some very fine set of points, I can still jump around because I know every time I do T0, I move to the left. And so it still looks very unpredictable. Okay, so now there's a way to think of this in the dynamical systems way, so-called iterated function system. So that's something that Barnsley and others thought of. So you can think of a mapping, which is a mapping that if you have a subset U here of the interval, that it maps to the union of T1, T0 of U, union T1 of U. That's basically mapping E0 into E1. It takes this copy, and I can keep mapping this. So this is iterated function system. So I can try to kind of understand what happens to this. So where does this live? Well, this lives on, this is a mapping that doesn't act on points, it acts actually on subsets of the interval. So I can, for instance, I make an abstraction here. I look at compact subsets of the interval, and I now have this is a metric space, for instance, with the so-called Hausdorff metric. So Hausdorff metric is a metric that measures the difference between sets. And so how is it set up? The Hausdorff metric set up is that we have a balance between two types of so-called semi-Hausdorff distances. And what is this semi-Hausdorff distance? It's a distance that says it's the infimum over all points y in a set capital Y, the difference between supremum over another set x. So how does that work? So I have a set x and a set y, for instance. It sits inside, just for as an example. So what is now the d? The d is y. It is you take the infimum, you take the difference of points between x and y, so you take any pair of points, and you look at this distance, and you look at the infimum over all y given a certain point x. So take a point x, and let's look at the closest point. Then I have a certain distance, that's the usual Euclidean distance. And then I look at the supremum over all points x in the set x. Right, so here, in this case, is positive. It's some kind of like the largest distance, probably something like this. If I do it the other way around, with this kind of distance, this is not equal. That's why so this is in general not equal to dyx. Because if I first do it for x, and then take y such that we have a minimum, then for each point y, of course, we have a point x which says immediately on top of it. So this guy will be 0, and this will be not equal 0. So then when we compare these two sets, we have to do these two measurements, we just need to take the maximum. And the statement is that if the Hausdorff distance is 0, then basically the sets are equal in some sense, in terms of Hausdorff metric. So it's a reasonable, very canonical metric for sets. And so we use it's built on the usual Euclidean metric, sits here, and just get basically try to compare to two sets. So if I look at this map, this that I just gave also on the board, then you can basically kind of see what it does on this metric space. So this is a metric space which is both. This metric space is a complete metric space. And then you can see that there's a contraction on this metric space. And as we know by contraction mapping theorem, and I hope that you know that, but if you have a contraction on a map, it's something we have a ellipsis, a map ellipsis smaller than 1, then we have a unique fixed point. So everything attracts exponentially fast to one point. And that's the attractor. So in this case, the attractor is this Cantor set, and it's the fixed point of this map. And important, of course, to show that this is a contraction needs some work. So if the map T0 and T1 are contractions, then so is this map capital T here also contraction. And that's an exercise. And I guess that anyone who needs to do anything for credit, maybe this is a nice exercise. You just have a look at how to do that. It's a few lines. It's worth not doing. But it's not the main aim of the lecture to talk about these kind of problems. But I just want to make sure that you see that there's actually some kind of control on this problem here. And also, if I vary this game a little bit, as long as I keep contractions here, I know that everything condenses to a well-defined set. It's a fixed point under the contraction in this metric space of complex subsets. Good. So now what I have is I have this point, I iterate it, and it condenses to an object that I know about. And so what happens with this point? Well, it also kind of comes close to it, of course, because you can see here that if you take any initial condition after n moves in the game, and of course the distance between x and n is smaller than 1/3, because what is 1/3 over n? That's precisely the gaps. So the gaps, it goes kind of closer into the gaps, and the gaps get smaller at every stage. So the distance between these points gets close. So you have actually the subtraction to this set E, because E is a Cantor set. That's a very sparse set. But my point actually goes and converges closely to this Cantor set. And so that set is a. So we have the set valued system where we take intervals and I map them down, converges to E. Individual point also goes close to E in similar fashion. No surprise. Okay, but now I want to understand a little bit more about the dynamics, and so I have to go look a little bit under the hood of the system. And so what I'm going to introduce is some symbolic dynamics to kind of encode what actually happens in dynamics. So I have the natural symbols, zeros and 1, for these maps that I use, and I'm going to basically make a coding of my set E, which is here the Cantor set, in terms of those symbols, which tells me, gives me an address actually where I am in this set. Okay. So this will be useful to understand what happens with the dynamics. So you have to bear with this for a little while. So what do? We take space sigma 2 plus, and I define this to be a set of semi-infinite sequences from 0, 1. So what is it? An element of this set is just an array of zeros and 1s, like a binary sequence. It's infinite on one side. And so there's the number 0 and 1. Okay. And I'm going to define a set U with some finite index address, Wn minus 1 to W0, or so omega n minus 1 omega 0. And as the images under these maps. In particular, U0 is just the image of the full interval under T0, so this is U0. And the image under T1 is U1. Right? Okay, now the next level, so T00 is the image under T0, T0. So this guy is called U00. Then I have an image T0, T01. So T0, T00, T0.
Second vector E2 must be U10.
Yeah, U10 is right. This U10 goes the other way around, etc. etc. Yeah. So just how do you define this number? Okay. So then I have a property that if I let P with some symbol acting on this set, what happens is just kind of add a symbol to the set. And of course, En is just a union of these symbol indexes. So I have a kind of addressing system where the first symbol says is that a single way? So I again have to read the sequence from the left. 0, 1, U 1, 1, U 1, 1, and U 0, 1. Okay, so now I can think about probabilities of these sets. Yeah, now I can think of probability, and so I have, because I have this object, in some sense there's a chance that I end up in one of these pieces. So I would like to propose that we kind of basically describe the chance starting from any point here to arrive in any of those pieces. That's not so difficult because it was chance a half to get here, a half to get here. And then to get here, of course, is a half times a half, so a quarter to get here, a quarter to get here, and that's etc. That's all not so surprising. So you have a half to get in T0, half to get in T1. Similarly, I have the chance to get in some of the subsets with n symbols, and the chance is 2 to the minus n. Okay, so now it's natural to think of this. Hey, this is kind of interesting. So I have on my Cantor set, which is some kind of a very sparse set of points, I have a certain chance to arrive in part of this Cantor set. And this chance is basically given in terms of these intervals, just as 2 to the minus n, where n is the length of the interval. So I can take any part of this Cantor set. I take the intercept and let's say how big is this interval, and then on this size of the interval I can see what the chance is that I arrive there. So there's some more information. And basically, so the problem of course is that this Cantor set goes down to points, but the chance to arrive at any single point is 0. It's 2 to the minus infinity, it's 0. But of course I can take a small piece. And the small piece carries some information. They say, well, I don't know exactly which point I arrive, but after 100 steps, I get a very small interval, 2 to the power minus 1. Yeah. So of course, we want to kind of create some kind of function, and this kind of function is a measure, and it's a probability measure. So it's a function that actually measures what's the chance that we're at somewhere. But of course, it's not a real function, because on every point in the support, it's actually 0, but you have to kind of look at this kind of set. So this is a mathematical concept, and I will not go too deep into it. You can follow all courses on measure theory, but it's measured. So what is a measure? It's something that's non-negative, such that the empty set has 0 measure, and the measure of a countable union of disjoint set is equal to the sum of the measures of this disjoint part. This is basically the definition of measure, and then you can make it as complicated as you like. In this case, it's very easy. So what do we have? We have the measure defined as a measure 1, which is just the length here, or the back measure of this set. And then when I go, I just subdivide the measure, like mass, half here, and then half, etc. And so it's well known that if you get this principle, this defines a measure on the limit set. So by the so-called telescopic principle, it's basically because you push the measure from the large set down until all the tentacles, and you just preserve the measure, no problem. And so this is a very consistent way you can do this. So we have a probability measure that sits on the set P, which is a Cantor set, and it has total mass 1, even though each point has mass 0 in some sense. Yeah, so this is, so what does this say? It says precisely what are the chances to be somewhere. Okay, now the technicality is that in order to understand these measures, we need some kind of like the objects on which this measure sits naturally, and this is called sigma algebra. And in this case, the sigma algebra just consists of all closed and open subsets and their complements of the interval. So this is all an abstract concept. So for a measure, we need to have some object on which it's defined, and the measure here sits on this on the subset. So basically, the important thing is measurability. If I give you any of those sets, a closed set or an open set or complement of countable intersections of closed or open sets, then I can tell you what the measure is. If I find some other set, which is nothing of this, then I can't tell you what the measure is. The measure is only defined on such sets. It's just a technicality. In this case, it's quite natural concept. But again, that's part of a course in measure theory. Anyway, but I wanted to keep it as low technical as possible. Just a simple example. We do a simple game, and we just get some object. The problem is I get an object which is complicated, so I can't avoid talking a little bit about things which are maybe counterintuitive. Okay, but now I can think of it as if you have done a course in probability, and probably have seen a Markov process or Markov chain or something like that. So we kind of describe, in some sense, the motion of a point x on the interval, and I'm going to the things as a probabilistic process. That's not my idea. Because I saw that was probability, and having done some elementary courses in mathematics, I said, I know what I need to do. I need to do Markov process. What does the Markov process basically says? It basically talks about transition probability. I say, what's the chance to go from x into the set, into this set, and I can describe it basically that the chances are half if I'm in this set, and the chance is 0 otherwise. Because I know precisely which set, because this set is mapped into two sets. It's set in this guy on the left and to the right. If it maps exactly this one, the chances are half, and otherwise not. And if I'm out of this set, I can never map into it. Okay, this is of course defined now on this subset, and of course I can tailor this down precisely to the way. So I have a well-defined set of transition probabilities from a point x into any of those sets where I know the measure. The probability measure of being there, if you does it by hand. Okay, so now what's the idea is to somehow use this Markov process to push forward measures. So I can say like, well, I can say I push forward one point and I want to go where it is. But there's another way of looking at it to say, well, I take a distribution of points. So say I have a probability distribution on this interval, and say, can I push that down also to this set? Is there a way that I can start with a measure, which is a probability distribution on the set, and push it forward by dynamics? And what would happen? That's basically the idea of the Markov process. So I go in a completely probabilistic description. I don't anymore give you one point. I give you basically just a whole distribution of points. So I say, well, I take a point here with a certain chance, which is given by probability distribution, then I push it down forward. The dynamics and say, what happens? Okay. Good. So technically speaking, again, you need some kind of a measure that sits on this so-called Imperial sigma algebra. I take an integrable function, and I have this stochastic process, which is some kind of my game, and then I can transfer this in some kind of implicit way, because I can say how integrals with respect to this measure. If I measure the measure that sits in a certain set, I can see kind of how this evolves under time of this operator. So I use a transition probability. F is the function which I measure something, could be a characteristic function. For instance, measure if I'm in a certain set or not. And then I have to integrate, and then I integrate over all positions. And then what happens if I take this measure here, then it goes to a new measure after one step. So it's just pushing forward the measure. It's just basically taking the measure, pushing it forward by dynamics. So this may be a bit of an abstract setup. Maybe it's easier to see it in the yeah. Okay, we can do it this way. There's another way we'll do as well. So maybe an easier way. Okay, if you just do this formula, let's follow my notes. So this is the formula. So how do you take that? If I just take here the characteristic function of some set, which is just this one of these sets on which I could measure naturally the dynamics, then if the characteristic function is put in, then this integral, this measure here, is just the integral of the probability distribution, the chance score of x or u, with respect to the measure. Now if I calculate this, if I take here u, this set, then I have to put this chance where I get into. Well, it's just basically a half of this other set what I had before. And if I integrate that, I get just the measure of this set. And the measure of this set is just this guy here, so times a half. So this is actually what we already knew in some sense, that when we push down the measures, in this line, you basically end up with measures that go half of the one before. Because half of the measure goes here, half the measure goes to another one. As another way to then express this directly is an operator on the measure, and we do exactly the same. And this may be another kind of way to express this sort of Markov operator directly on the measure, and that is you define this map M, and it's just a chance to do something times the action push forward on the measure, the same as we just did, and you get this formula, that's a half times, and if you act on the measure, you have to act on the inverse of the argument, and you get basically this weighted sum, and only one of those two will contribute to this thing. Okay, so we can push measure forward, and the question is like, does something converge? Is there something that if you can keep pushing measure forward, does it go to somewhere? We know that if I look at the whole set, and I push it somewhere, then it will go somewhere. It will go to the set E, which is Cantor set. If I take one point, I know it doesn't converge because it just keeps jumping left to right and no idea where it goes. But I say, like, if I take now a measure and I take this Markov process, which basically keeps this kind of creates a distribution in some sense, will that go anywhere stable? Right, so this map M that does this, that pushes the measure, is important to know that this map is a linear map, so it looks like maybe easy. Linear maps seem to be easier, but of course the trade-off that we have is we have, of course, an infinite dimensional space, so linear maps and infinite dimensional spaces are not necessarily so easy. Okay, so the question is, can we do something there? And so the next statement that I want to make is that the probability distribution that we just defined is actually a fixed point, is actually invariant on this Markov process. So what is an invariant measure? It's just the one that sits there. So it is a measure that if I put it on the set and I push the measure one step forward, it just stays exactly the same. It doesn't really redistribute. And so clearly, if I take a measure which sits a bit strangely on this interval, and of course, if I push it down and forward, first I know that all the measure will go sit on these pieces, and then it will just kind of shuffle in some way. But maybe there's a measure that sits there and just kind of stays there, and that apparently is the measure that I define when I push this game with half, 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 and all the way down. Okay. So this is precisely the set. It's kind of invariant. And how to check that? Well, you just have to show that M acting on this measure is the same. And how do you do that? Well, you just basically, it's enough to look at just these subsets, because everything is built here from this subset. There's no mystery. Everything that we know is from the subset. And you just compute it. So you have the act M on this guy, where U is this. So you this is the definition. Then I just see what the inverse is of this map. Well, the inverse of this guy is that I have to add a subtracted symbol, and that's what I add a symbol here to the left, right? Subtract the symbol, and I get a half. There's only one of those that applies, and then I get precisely this thing, and I get that times a half. So here you get basically factor 2 because it's a shorter sequence. Get a factor of half because only one of those applies. So it either comes from T1 or T0. One of those only applies, and then I get a factor of half, and then I get precisely the same measure. So I started with something of measure 2 to the minus n, and then it's again 2 to the minus n. That's quite elementary. Not so surprised, because the way I define this measure is precisely by understanding how this measure maps around. So it's not so strange that somehow this is actually invariant. It's of course always, the chance to be here is always kind of half, because if I don't know what initial condition I have, this was the only thing I knew. So the nice thing about here, when I constructed this measure, it didn't depend on initial condition at all. So I'm not so surprised that this is a invariant measure. Okay, now we can actually formalize this. So this Markov process. So now we have these measures, and we want to push forward measures. And now we have a complicated metric on the space of measures. These are space of probability measures on 0, 1, well for probability measures. And it turns out that if I look at what m is in this metric, it's again a contraction. So that's very nice. That means that actually it has a unique fixed point. And if I keep acting with this map m, it just basically exponentially fast converges to this unique invariant measure. So again, this is a bit of an exercise to work with this thing. So this is this metric is consistent with the big topology. That means that two metrics, two measures are the same. Basically, if they lead to the same integral for continuous functions. Good. Yeah, so this is a very standard metric that people use in this case, and it works very nicely. Again, it's an exercise to check that this effect works. I will not do it here. Good. So now we have our kind of little chaos game. I know that my orbit somehow converges to an object which is a Cantor set, but it still jumps around in a crazy way. And it turns out if I look at it probabilistically, I can say, well, if I just look how a distribution of points converges in some kind of like probabilistic sense as a stochastic process, where I keep basically all options open, then actually this measure pushes forward to a fixed point. So that means I have a well-defined, some kind of like probability measure coming out of this dynamics of pushing measure forward according to the stochastic process. Okay, so what I need to say now is that what I did is that what you usually do in your probability theory classes. So you have some stochastic process and say, stochastic process, let's set up this kind of Markov operator. Why not? I don't know anything. I want to know where my point goes, so I want to kind of get some impression where it goes. And then you set up this thing, but it's not dynamics. The dynamics of the Markov operator is not the dynamics of the system. Because my Markov operator pushes a measure forward to a fixed point, and my point jumps around erratically from left to right, and does something completely different. So, where maybe in your probability course you would say end of exercise, we found that there's an invariant probability density. Actually, I'm not happy now. I'm not happy enough because I don't know what the dynamics is. I only know that there was some statics. So technically speaking, there's a word which often doesn't appear, which should appear here clearly, that in your stochastic process, you model the so-called one-point process. So what's the one-point process? You basically model like where one point goes. And the only information you get probabilistically is actually where this one point is. So if you ask like how often does one point go somewhere, then you get an answer here. You say like, well, if I look at the part of the Cantor set, and I have this measure, then it says, oh, the probability to be there, but the one point is there. But it doesn't have any dynamical information. It's not dynamics. When we do dynamics, we usually like to say like, well, if I have 2 points and I start somewhere, then there's evolution and the points go somewhere and maybe they come back to each other. And maybe they do something else interesting. All this information is lost. So my original equation of motion had dynamics. I just say, if I have a point to go somewhere, if I have 2 points close to each other, I can compare what the points close to each other do. In the stochastic process, I have no such information. It's all gone. Right? So, the stochastic process that I just defined is not the same as my dynamics of my chaos game. Very important. Very important. So it is a reduction of that model. I extract from this model, which is a dynamics model with some random component, I extract some information about what one point does. And then I write it down as this Markov process. Very important. That's crucial. Yeah, so I just have to emphasize that most problems, when you look at them, and in theory, there's a dynamical systems problem where people do very complicated analysis of orbits and how things relate to each other. You add some noise, and what people do is they basically do this. They say, noise. Markov process. And it's like full Fokker-Planck equation. And then they solve. End of exercise. Solved. Like you cannot do anything more. Okay, so the question now is, can we do something more than just doing the statistics? With the Markov process, we just do statistics of the one-point process. So the question is, can we do something more? Okay, so what do we more? It means we have to get more control over the dynamics. So what I'm going to do is I'm going to formalize this coin the coin tossing event a little bit more in more detail. So I'm going to give the coin tossings this symbol sequence. I also called here omegas. It's the same numbers that here. That's just my index. And I take the set of all realizations of coin tossing. And I can define the cylinder set, so-called a group of coins. If I have a certain coin tossing with a certain kind of set of symbols, that was a cylinder set, and I define a probability measure on this space sigma 2 plus, and with some sigma algebra which is based on these cylinder sets, by basically defining what precisely the probabilities in each of these sets, and just 2 to the minus n, because it's the probability that I have such a specific event. Right? I say like 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 5 times 0, 2 to the minus 5 chance. Because otherwise I would, there's also a chance that I throw other numbers. So it's a very natural probability measure on this thing. Okay, so what is now the noise process? I now describe the noise process as basically a reading of the sequences as a dynamical system. So I take a sequence of coin tossing, I don't know what it is, but let's say that it's like in your computer, you have a random thing in your computer, the computer generated already a random number for you, it will just read off the numbers. So what I do is I read the number, I say like sigma plus of omega, what it does, it takes the random number, or some kind of sequence, and it just eats the first symbol, so the shift map. And then the second number becomes the first number. So some kind of probabilistic process cannot be modeled by I just want to read zeros and ones, and now for instance I use the first symbol and then I shift one further, and then the next time I use the first symbol, that will be omega 1, etc. Okay, so now this measure, this map sigma plus, turns out to be measurable. Measurable means that every measurable set has a measurable inverse. And this is also invariant under this shift. Not so surprising, I just shift symbols back and forward, and then I end up with invariant. Here's a calculation, maybe because of time I will not spend too much time, but you can just basically add on the things. You say you add this sigma plus on this measure, and it acts as the inverse of the argument. As always, well, the inverse of the argument means there's two different symbols can go in front, a 0 or a 1, but these sets are disjoint. And if it goes into the cylinder set, then if I take the disjoint set, the measure of this plus the measure of that. But these measure of this, these is this is a half times the measure of before, and this is also the half time before, and then 2 of those sets, 2 times the half is 1. And then I have just the same measure. And so this is a measure preserving transformation. So I have a probability measure on my symbol space, and my reading procedure nicely preserves this measure. That's a good idea. And now I say that this actually is some kind of dynamical model of my noise. So this is just not, so in the stochastic process, we basically convoluted all the possible futures. So you said like there's a half chance to go here, half chance to go there. But if I have a specific time path, I describe the path as a dynamical process, whereas there's a specific future, this is coded by omega. Omega is the one realization of the random process. It's not actually convoluting all random processes together. Of course, admittedly then, we jump from left to right. That's just the nature of these. Okay. Okay, so now we come to this kind of dynamical formulation of the process, which is actually the game. This is not, I'm not reducing it, I'm just basically saying what it is. That my dynamics is given as a map on 0, 1, but also on the symbol sequence space. So my input is random, comes from this sequence of 0s and 1s. I don't know much about it, I just know that it has a certain, it comes basically IID from this kind of symbol sequence. And then what I do is, given omega, I give a thing what it does. If I have such a point, it maps here with the map, where it's basically reading the first symbol and acting the map, so this is 0 or 1. And on the omega, it just shifts. The omega throws away the first symbol, I don't care about it anymore. It's like you're reading a ticker, you know, it's like the Turing machine. You're reading a ticker tape, and you read a symbol, and you just don't care about anything else. You read here this and this. So this is called so-called co-cycle, or skew product. Because what happens is this guy, the first part of the equation on the interval depends both on the omega, which is some kind of, and on the x where you are. But this process doesn't depend at all on x because it's just boring reading the line of omega. So the second line is very boring. It feeds into, it's like a driven process. I have a process on 0, 1 which is driven by this shift on omega. Okay, now I can use certain kind of notation, and one should kind of understand, of course, that this is a product. But then, if you want to decompose the product, you have to also take care of the fact that you shift the right way in these omegas, because it's a sort of non-autonomous system, and so you have a driven system. So this is really the game we play. The game we play is really like this. You could say, like, well, I pick omega from the symbol space, long sequence of 0s and 1s, then I'm going to play this game. 0, 1, 0, 1, 0, 1, 0, 1. And this is not the markup process that I first described. Okay. That's how here I just said this. So we have this co-cycle, and we call the dynamics on the omega, we call it so-called the base dynamics. The base dynamics on omega sigma 2, and it feeds into the dynamics on 0, 1. But not the other way around. What happens here doesn't influence this. This is just a process that works by itself. So it's rather boring, but it feeds into this process. That's a so-called non-autonomous system. It depends explicitly, in some sense, it depends explicitly on time. You can think of this as some kind of time model of the time, sigma 2. That process. And sometimes we think of this also kind of as noise. Good. So typical, as I said, typical dynamical systems question to ask is what's the behavior of infinite iterate. But I know sometimes that's difficult. So I can ask that for the whole system, or I can ask this about the fibers. I can say, like, what happens just in 0, 1. So we sometimes call this the base. You can think this is just the base space, and we take the 0, 1 fibers on top of it, we move around, and the 0, 1s see on top of it, so we call fiber and base, like a fiber bundle. Okay. So the problem is that usually this F, this map on the base doesn't converge to anything, so I just formalize it here. Of course, it goes to a fixed point if you only do T0, 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 because it's just strings. Or I do T1, 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 T1. Or I do a long sequence, and in the end I do only 0s or 1s. Then of course I just always focus, I'll go to one point. Otherwise not. Also, actually, if you have a periodic sequence, if in the end your simple sequence goes to 0, 1, 0, 1, 0, 1, 0, 1, then also your point will converge to a periodic orbit of period 2, because it will jump between 2 points. It's just because you have the contraction property, everything will converge to something nice. But this is very unlikely. If I just draw an arbitrary element of omega, it will usually not be eventually periodic and also not eventually constant. So these things are not interesting. So for that reason, when I look at the dynamics, I'm not very much interested in behavior which covers some kind of zero p measure of events on the simple sequences. I'm not interested in eventually periodic or eventually constant sequences of points, because this is not really typical behavior. And so when I'm interested in the dynamics of this random dynamical system, I would like to have some properties which are basically hold for good positive measure, for some kind of good measure set of noise realization, and definitely not of zero p measure. So the conclusion is we should not expect really simple asymptotic behavior in this chaos game. Good. So in the absence of this any sensible convergence, people thought about some other things to do, because it's not a good question. So they asked, like, where do I go in the future? It's not a good question. But you can ask another question, which may be a strange question. What can I do? What could I do if I know something about the past? And if I say that I started in the past and I converged and I evolve to today, and what if I take the limit that I say, well, suppose that I started further in the past and I come to today, or even further, or even further, or even further. It's called pullback dynamics. I start at a certain point in time. So here's my time. I say, let me here let's say time 0, for instance, and here time goes to minus infinity. So I can ask myself the question. So usually we ask, given an initial condition, what happens if you go to time to plus infinity? This way. Yeah? But now I'm going to ask, suppose that I give it a certain initial condition here. And this is a minus t. Say what happens with the flow on the dynamics until it happens till time 0. I say, well, anything could happen. Okay, but maybe I take this point x and I take it a bit more backwards. And then I let it flow all the way to 0. And maybe I like to even put it more backwards. Let's let it fly all the way to 0. Of course, here our system depends explicitly on time. Right? But this is going to be explicitly depending on the past. Now the good thing here is that, as we saw in the chaos game, when I keep iterating, every time I do T0, T1, I jump to the left and to the right. So I don't like to add things to the future, because in the future I can always get left and right. But what if I take my time to minus infinity? Is that like a long time ago, I did T0, T1, T0, T1, and maybe in the very long time I add another T1. But actually it's very clear what here happened. My last throws were T0, T1, T0, T1, whatever. Always the same, because it just depends on the time. Right? So I can see already I'm a little bit less sensitive. Because the most important, the most big scale of where I am is determined by the last iterations. The fine scale is determined about the iterations a long time ago. So who knows, maybe this works. Right? So here's what I do. I take the nth iterate of x, sigma to the minus n omega. It means I pull I go into the history, and I let it flow back forward. And I then take n to infinity. So pullback dynamics. Very strange concept. And it's basically grown out of the fact that we don't know what to do else. Right? Okay. So of course, in order to do this, I have to invent the past. I didn't do that. My time had only positive times, because I was my head in the wrong cloud. There was in my head in the cloud that I have to only look forward. I'm interested in things for the future. And that's why I say, if I do coin tossing, I'm interested in the future coin tossings, not in the past. But if I do this kind of stuff, I actually have to know what happened with coin tossings in the past. So I'm going to extend my space of coin tossings to go to the past and to the future by infinite sequence. I can ask which coins did I toss 100,000 years ago. Also important, maybe. Okay, so I extend this time space, and then of course I can do similar things. Again, I have a shift space, and I now put a dot somewhere. The dot is today. So the dot means that omega 0 is my thing. This is the omega from the past, and these are the omegas from the future. I don't throw anything away. And this is, again, has a nice measure. It's invariant, and so on and so on. And this is very canonical concept. Just the same as we did before, in a very trivial way. But I have now the symbol sequences on both sides. I call it sigma 2, and I have a dot somewhere because I have to know where I am today. And then I have the same kind of map. Everything is the same. So I have a good concept. Another question is like, does this limit phi n x sigma to the minus n exist? Okay, now so what we can do basically this computation. So now we can do the computation of this thing. You take 0, 1, if we take the inverse, I get an element. So I take this element here, And then I take the next element, and what I do, I just kind of add a symbol to this to these things. I can see that I just have add symbols. When I go to the pullback attractor, I add more and more symbols. So the first one I get 0, 0, 1, then I get 0, 1, 1, 0, 1, 2, etc., etc. So I get like some kind of fine detail in this map. So it turns out that if I do this dynamics, I get precisely these kind of sets. But these sets, I knew what they were. These sets are precisely these smaller and smaller sets that I have in my Cantor set for cover. And I also know that if the number of symbols increases on the subsets, that they shrink, they shrink, they shrink, they shrink. So I see in some sense that my pullback dynamics is very nice. Actually, it does converge, because if I take an infinite sequence here, then I can precisely do an endpoint in this Cantor set. So the limit of n to infinity of this pullback thing exists. It is independent of x, and it's precisely this address in the Cantor set. And so I call this guy A omega. A omega is the pullback attractor, depending on the past. It's a single point in the Cantor set. So if I knew everything about the past, then I know where, if I started in the past with some point, where it would converge to. So things from infinity to the past, they converge to something. That's quite surprising. So we have no idea what happens in the future. Well, I know something. I know that I map around in this set in the Cantor set, but I don't really have any control where I am. But if I say from the past, I say, well, what would happen to our ancestors? Then I can say, well, but I know all the. Then I can take into account of these events, and I know that I converge to a certain point. Well, I converge if I go further and further back in time. So you go further and further back in time. So you have here a sequence of times. I start here with some set or some point, and it will go straight here to a point in E. And this is this set. With the insert address. So if I know only some parts of the address, I also know something, and know that it's in a subset. Right? And if I then know more symbols, then I know it's in a smaller subset. Okay. So it's important here that this course doesn't depend on initial conditions, just because the special setup of the system is very uniform. And I didn't do any probabilistic estimate. I just follow a path in the thing. So if I know something about my path in time, my point tossing, then I know that I have convergence, and I have so-called global pullback attractor, or this chaos game, of course, with a certain realization of the path. Yeah. So this is more dynamics. So now I have an attractor. So in dynamical systems, it's like something like, for instance, we have a planar vector field with an attracting equilibrium point. We know that if you go time to infinity, everything spirals into the equilibrium. So then it's autonomous, it doesn't depend on time. Here the best thing I can do is I go to the back of the time and I converge forward. So we have a global pullback attractor. Okay. Cool. Maybe we should have a quick break, because we have to throw maybe 5 minutes or so. Yeah, and then I'll continue. Okay. Continue. So what we just saw is that so usually in dynamics I'm interested in what happens in the future. And although I could do something in some kind of probabilistic way on the Markov process, and I really like to kind of understand things more from a trajectory point of view. I really want to go where one realization of the system goes. Like really in the field game. And so I just found out that I can do something if I focus on the so-called pullback dynamics. I take a certain initial condition, I put it back in the past and let it run forward. And I take the limit of taking very far in the past and going forward. And that gives me precisely this elements here. So if I add more in the past, I get a longer simple sequence and I know exactly where I end up. So the more I know about the past, the better I know where I am. Not so surprising. Not so surprising to think of it. It's really concept, and it's called pullback dynamics, and the object that we converge to is called the pullback attractor. Okay, so now the question is like, what is the pullback attractor? Tell us about the nature of the forward dynamics. So we know that the pullback attractor of the chaos game attracts uniformly, because if I take this thing from here, it actually has a certain, it's just like it gets attracted to the set. I know exactly which part of the set it gets attracted to. So this is a very nice exponential convergence. Very simple example. As I said, this example is beautiful. It's not entirely trivial, but this attractor looks a bit complicated. But you can compute everything. So this is just precisely true. So we have this convergence. And of course, for every 2 points in the set, I have the fact that this always contracts. So every 2 points in the set always converge. But this is true from the past. It's also true in the future. Because it's just always 1/3 and then maybe some translation. So we have some kind of aspect of that points are converging to each other, but they're not necessarily converging to something. Because in the future, they go to reds and lights or whatever, but we go all to something. So this is an important thing. And so the past is unknown, but not as always lost, because we have some relation. Of course, we know that if we know something of the past, we know where we are, more or less. And so as time progresses, we learn more about the random pullback attractor as we increase our knowledge about the past. So if we go in the future, we don't learn about the future, but we learn about our past. So some weird way, if I go forward, I know more about the realizations, and it gives me more an idea of where I am. So if I know only 10 years of history, I don't know where I am maybe. I would say, well, I'm somewhere. But if I go down 100 years more, I have more information, because when I look past and forward, I must be in a very small sense. So you learn something about where you are by knowing more about the past. It's very typical of this kind of behavior. Pullback. So it is true that, of course, and then also we know where we are in the future, because it limits, of course, to some extent also where we are in the future. But not so much, because every time in the future I can do T0, T1, I can jump left or right, and it seems to be arbitrary. So the important thing is this: so every trajectory converges, in some sense, but to a moving target. So it's a bit like, so it's randomness. We have a point, and I want to try to follow this point, but the point jumps around, and I just follow like crazy this point. It's only when I keep the point fixed and I increase knowledge of the path, then I know that actually I'm converging to this point. But if I freeze the point in time, then of course I converge only to this one point. But depending on the future, then it moves around. So it's a bit like an erratic following of something in the past. It's completely coherent in the view of this randomness of the dynamics. You should not expect to converge to some fixed object if the equations change. It's completely not what you should expect. So we have a moving target, and what we do, because we have uniform contraction, we just converge to this moving target. And where is this target? Well, we know more about this target if we know more about the past. Okay, so that's the technical definition. So this object A, which is called this point, I call it attracting random fixed point. It's precisely the same thing as a fixed point in an autonomous system. It's just now it's a moving target. It's not a fixed target. And I need some technicality. So I will reply that A is measurable. That means that measurable set here has a measurable pre-image. If something is measured here, can be measured there. That's important. If that's true, then I call A random fixed point. If it has this good property that if you act the omega on it, it precisely goes to the next object in the set. And this is of course here the case, because my sets are just the sets of the simple sequence. I know exactly how my dynamics act on it, just adds a symbol to it on the front. And so if I have some sequence here and I do T on it, T1, then I get the same sequence, started with 1 and then the rest of the sequence. That's precisely this thing. And so that's of course then also that's a moving target. But the target moves. A moves under the dynamics as just the shift. And the shift adds a point to the future. Because the dot goes to the right, and the future gets an extra information. You have to be careful a little bit, because if there was no measurability, then I could say that every orbit was a random fixed point in some sense, because I could of course just define this object A in such a way that I take a point, because it depends on omega, and say if I shift it, I get another point, and I just call it, I define it as this object, and just carry on. And so without measurability, it's important somehow. We need some measurability here on this object, otherwise every orbit could be called a random fixed point. And that's not, because it's not really how to define this function in general. I could start at the point and define all other points in this way without anything information. And so why is it here measurable? Well, I take the A inverse of this set, then I get basically some sequence where we precisely need to have these precisely the simple sequence that fits with these things. This is also measurable. That's also like a symbol. So because we had a symbol sequence to define this set, but also the symbol sequence to define these things, and they were both measurable. So it's very nice, it's a nice correspondence. If I have a measurable thing in the symbol sequences, it's also measurable in my space. Good. Okay, now we finally just satisfy this property, check that this property is true. So T omega of A omega, what it says, well, this was the pullback limit. I add T omega on it. What is T omega? It's just taking the first symbol, that's T omega 0. I let it act on this one. This was the definition of this object. Well, this is the same thing as the limit. You just take the T0 inside here, but now I see this longer sequence. This is again just defined as the previous one, and then this is the sigma of omega, because I add the omega 0 on the shifts, and because I had the symbols. Sequence, and I put sigma on it. What happens with sigma? Sigma happens that I have the same sequence, but then the dot changes one position. Here's the dot now. So this sequence goes, so this is just a dot shift one point. That means there's one point added here that precisely fits into this. So this guy just gets an extra symbol. But very obviously, this works. Good. So now, I'd like to philosophize a little bit further. So the relationship is actually some kind of like a semi-conjugacy between T omega, which is the map in the space, 0, 1, and the map sigma, which just lives on my base. And so my base is the sigma, and then in the fibers I have the T. And now I have a relationship with A of omega relates A of sigma. So this is a so-called semi-conjugacy. It's a relationship between sigma and T omega defined by A. Okay, and so we take A on A maps, of course, into the space 0, 1, but let's map A into E, into the Cantor set. So let's define, then it's surjective, because every point in the Cantor set has an address. So it means that all addresses. It's not necessarily injective, because it only depends on the past. So if I take a symbol sequence here, I can of course ignore everything on the future, because it says nothing about my point. And so because A depended on the past, not on the future. And the omega has information about past and future. It's like my complete coin tossing sequence. So these things are equal to each other, two omegas, you can have different futures. It doesn't matter what the future is. So it means it's not injective. But of course I can reformulate now. I can say, well, let's just forget about the future. And I go again back into a half infinite sequence time, but I take the future on the other way around, I count backwards. And so I take the backwards times and model them by a half infinite sequence. now I have a map which now is injective, because I have for each symbol unique set in the Cantor set. So now it's invertible on its range, and it's also measurable. So with this set, and I have conjugacy, right? So I have a proper conjugacy. Now let's see. So I redefine these things as a positive time on the past time. And on the past time, then I have this with the shift also I have this kind of proper conjugacy. So I have a conjugacy between these two objects with this 8 billion. So the thing that says that in some sense that the object A omega has something to do with the dynamics. There's some relationship between them. And its effect can be better. Conjugacy is a formal relationship, which is an invertible transformation. It's a bit nicer if it's topological, it's continuous. Then we need to have the topology. Of course, the natural topology on 0, 1. And we can also have a natural topology on symbol sequences just by the cylinder sets. And for instance, take a metric like this, it induces a certain topology where the cylinder sets are the open balls in the topology. So it means that the symbol sequences are similar around the origin. Then it turns out that actually they're close. Symbol sequences are close. If you take this topology, then you find out that this map actually is continuous. That if I take two symbol sequences which are close to each other in the topology, they also lead to 2 points which are close in the Cantor set. So what you get from this information? You get from this information that in some sense, the erratic behavior of the dynamics for the pullback attractor is also a reflection direct of the type of erratic behavior of the noise. So in some sense, the random dynamics is some kind of like image of the random noise. Not so surprising. If you have a very stable system, and I say that I impose a huge noise to it, and you look at the system, what it does, and you see some noise, you would say, well, you see some reflection of the noise in the system and in the object. It's kind of what you would think. You would think that there's a translation from the noise that you put in into the noise you see on the other side. And in this very simple example, with this uniform convection, what you see is that there's some kind of equivalence between the randomness of the behavior on one side and the randomness on the other side. Of course, if you take the right mathematical set. So there is a certain equivalence between the noise and the dynamics in this context. Not so surprising, but it all depends on the past. Good. It's just a digression. Okay, so now it's important because now we have to introduce some objects. So a probability measure for the co-cycle dynamical system, that's the system on the base plus the fibers, is called invariant if it's invariant under the action of the dynamics. So here's the dynamics of the co-cycle. So let it act on the thing, but what we do is that we take the inverse on the argument, and I want to check that it's the same measure. And so what you're going to check, what is the proposed measure here? The proposed measure is the measure from the random fixed point. So what I take is I take the base measure, just P measure, the measure that I defined before, and everywhere I put the point mass on the fiber. So that's schematically we have sigma 2 here with a measure P. And then we have fibers. And in each omega I have a point mass at A omega. So I have a kind of like a graph over this, with a strange space, but I have a graph over this space sigma 2, and in each fiber there's just a point mass. The mass is like that, so there's a point with mass and nothing else. So it's not smeared out, it's just a point. That's the attractor. And this is the mass, and I call this mass mu. And I want to show that this mass is invariant. What is of course this mass? So I of course this base is invariant. I know already because it was P is sigma invariant, and that's it's the Q product. So the sigma dynamics basically is independent of the rest. And I also know in the fiber that this is invariant because I know that if I act with this guy on fiber, I go to precisely the next point mass. just given by the shift of the omega. So there's a behavior in omega, and it jumps from the point mass to the point mass. And so this is going to work. That's a natural invariant measure, because I know for the pullback, everything goes back to this object, and then if I keep flowing it forward, it will be invariant. So let's see that, so I can do the formal calculation. I can just check it, but it's not such a surprise that this works. And maybe we shouldn't go so much into detail. There's this calculation here, but it seems to be obvious because I have the pullback limit, gives me a pullback attractor. Of course, if I now push this forward, the base is invariant, and the A omegas go to just the A of sigma omega. But all the A omegas are well defined, and they're all addresses in this counterset. And so the A omegas lives in the counterset E, and here we have this thing, and we just have to make sure that it's all nice and measurable. Okay, so we just check that this in fact works, no surprise. So this invariant measure is very different from the measure rho that I had that was smeared out over the whole set. And because this measure has some information about also the time behavior. This measure here basically was very different. It was basically something more like you take the projection of all these kind of atoms and you just plump them all onto the axis here. This is 0, 1. Or on E. So E here to the set. It's like just a condensed version of this measure. But now you have a lot of information of this invariant measure, also in the time direction, also in the direction of the point of the sequences. And that's a surprise. Now we didn't throw away the information on the time, and we have a much more richer picture of the dynamics. Right. Okay, so if I take this invariant measure, I can look at the so-called marginal. What's the marginal? The marginal is precisely just projecting all the measure either to one side or to the other side. I have two coordinates in E, or on 0, 1, and in the sigma 2. And it's not such a surprise if I take this measure here that is defined, of course, precisely. If you push down all the mass, it goes precisely to the measure that I already defined on my time space. That's precisely as I wanted, because I didn't want to have a subset or a zero measure set. And then the stationary measure I define is the marginal of the invariant measure to 0, 1. So the marginal is that I just push all this measure here and I push it to 0, 1 and just forget about this time. So what is that, technically speaking, the marginal of the measure, so it should be rho, no, mu to 0, 1, the invariant measure for the skew product is called the stationary measure associated with this measure. And if I push it forward, what do? I just take this measure and I just expand the subinterval u, which is here, and I just take the whole time, take all the measures here, and I just plump it all there. That's what I do. And then there's a calculation. And if you do this calculation, you see precisely that you just measure precisely when A omega is indeed in U, and you just add them all up in the right way, and you get the information of this guy. Right, and this is precisely the pullback measure, of course. It's the pullback measure, and U omega is pullback measure. Yeah. Okay. Now, but I also said, let's check it. The stationary measure actually is equal to the invariant measure of the Markov process. So this measure that I have is dynamically defined. If I push it to the marginal here from 0, 1, I precisely get this measure that is defined here for the Markov process. So if I lose all this information of how the dynamics happens, I get some kind of blurry picture, and that's precisely the same measure. So you can check this. You check again just basically on the element of the cylinder set. I take this kind of set and then do this integration. And so what you do, you have to basically take like this session. I have precisely which parts appear in this set precisely with the right symbols. So I put the thing with the right symbols in here. I count this measure, and if I count this measure, I get precisely the right number on it. So you can do this in several ways. So I have here two different processes. I have a dynamical system, which is a Q product, which basically is the real game. For the real game, I had some kind of probabilistic description of the dynamics of a measure which is invariant on the dynamical behavior. I had another thing where I said I did this one-point process, which often people, they do it, but they don't realize what they're doing. They say, like, I make an effective model of what the stochastic information is I have in terms of a Markov chain, and I look for invariant measure. Now, these dynamics are very different. This process of the Markov operator is not dynamics of the system. Very important to understand. It's like the Fokker-Planck equation, not dynamics of something. It's just an equation. So with this process, you can see what happens. It pushes forward with no information. But then I have a dynamical picture, and it turns out that if I take this marginal, I get precisely the same measure from here. So of course, this will be true under much more general circumstances. It's not always true, but it's quite often true under the right conditions. Now there's another technical thing, so I'm introducing some technicalities here on this example, some of this integration. So if I have a stationary measure of the chaos game, a mu invariant measure, I can do some tricks. First of all, I can look at the so-called disintegration of this measure of a set with respect to mu. So I take so I have the system, which is defined. So I have my base sigma 2, and I have my 0, 1. And somehow, so I have this Q product space, and I have a set A. And I want to know its measure. So how do we do this? Well, I look at the sets A omega, which are subsets of 0, 1, but they're in the fibers. In the omega fibers, if I fix the so the omega is fixed. I think omega is fixed. In this section is A omega. Right, and then I define a measure here, and this is on this fiber, and I call this mu omega measure on this fiber. So I want to disintegrate the measure of this set into a product, basically by the measure, this is the P measure here, sitting here, times measure in these sets. So I would like to write this guy in terms of an integral over dp, the base, over the mu omega, A omega, measuring the measure that sits on these fibers. And in the case of a random fixed point, precisely this mu omega is just an atomic measure. And so the nice thing is that here, so associated, this is mu, and this is the stationary measure associated to mu, and then this measure is precisely the pullback measure of the stationary measure. Yeah. So rho is the stationary measure, mu is the invariant measure of the Q product. This is the pullback limit of this measure. So what I do is I take, in this picture, I take here rho, sitting in minus infinity, and I push this to a certain fixed point in time. This gives me mu omega. That's my pullback limit. And then this mu omega precisely is the fiber-wise limit of this set. And I can disintegrate this measure in this. Okay, so that can be done for every invariant measure. And then, okay, you can prove this. So what you do is you take the, just do it for the example in general. So we have this kind of atomic measure. You know precisely which points these are. So we can just choose this, that the whole thing is true for a generator of the algebra. I take similar sets in both time and in space. and I know exactly what these guys are, because I know exactly where, when a omega sits in this set or not, because I know exactly where it sits in A. So this is a symbol in the set, so just comparing symbols. And if you then write down the integral, then you can just check the relationship. It's actually very computable, because every information is just in the symbol sequence. My point A omega sits in this set, if only it has the right omega in time. And so these things are kind of just, so you can just basically count all those things, and you see here precisely what's said. This says that this set sits in, A omega sits in this guy, and the time is precisely in a compatible time frame. That's precisely. Okay. And so this integration is often used, and it's a because this integration somehow says everything about the measure mu. So you can think of the measure mu of this two-product system, but sometimes it's more useful to think of all these disintegrations and the set mu omega e. So this set in omega, the time space for sigma 2. So this actually gives you all information about mu. It's just more information, because it also says how the measure is divided about the omega patterns. That's what we want to do. Okay, good. So, ergodic measures. Okay, there's a special property of measures, which is called ergodicity, which has to do with how we use invariant measures in dynamics. The famous result by Bldg, and I'll get to that. So let me first give the definition. So an invariant probability measure for dynamical systems called ergodic is every invariant set has either full or zero measure. So I have a set which is dynamically invariant as a set. If either this set has zero measure or full measure with respect to a certain measure, then I call this measure an ergodic measure. And so an example here, P is an ergodic invariant measure for sigma. P was an invariant measure for sigma with its full measure, or sigma 2. There's no invariant every invariant subset also for sigma, it had a full or zero, because for instance we have periodic points or fixed points, they have zero measure, there's zero P measure, so they're also invariant sets. Under the shift, the sequence 0, 0, 0, 0, 0 is fixed, because if I shift it, it's just still the same sequence. Problem is it has no measure. So if I take any kind of block of sequences that have some measure, then I'm in trouble, because then when they do not be invariant unless I take the whole space. So this is an important example of ergodic measure, and this is actually our preferred model for the time. We like to have, okay, we can talk about different classes of random dynamical systems. It's nice to have a random dynamical system where the base dynamics is ergodic with respect to a fixed probability measure. And we have a good time random process in the back, an ergodic process. And mu is also an ergodic invariant measure on this things with this marginal. And mu is an ergodic invariant measure of sigma, of phi, of the product block. And I'll prove it here, but this is the case. Good. And ergodicity is important. So why is it important? Because we have so-called ergodic theorem. So it's because ergodic theorem says suppose we have some dynamical system, some evolution with invariant measure, and we had some integrable observable with respect to this measure, then two things are equal to each other. One, this is so-called the Bldg sum. This is the average of the observation through G of my dynamics. So for instance, there's something going on in the atmosphere. I measure temperature. So G is measuring temperature, and I'm doing the average temperature. It means I add all the temperatures up, I divide by n, and I take the line limit to infinity. And this says this is actually the expectation with respect to mu of the function G. And what's the expectation? Is precisely this integral. The integral of y, gy, du, y. This is famous result of Bldg, and in the statistical mechanics, which is a very important part of modern physics. This is basically assumption that we understand something about invariant measures which are ergodic. And if we are ergodic invariant measures, we can do statistical mechanics. And also what we do in physical sciences is has the underlying idea. The big problem of mathematics is that are the systems really ergodic? And are the measures that we like to believe are they ergodic? And increasingly one understands that they're usually not ergodic. But maybe they're nearly ergodic, which is good enough for science. But the strict property is this, that we have this. So if we have this measure with a nice property, then we have this equality. So this is now it's, you see why it's so important to know the invariant measure, because instead of doing this computation, where we have to observe time orbits, if I know the measure, I can just predict what the expectation value is. I just integrate over this measure, and I have an expectation value, and I don't. This should be the same as this guy. And so sometimes what people do also, they try to produce numerically using these things, this is a measure. You say, well, you know, I can measure. For instance, you take here the characteristic function that says it's 1 in some interval and 0 everywhere else, and then basically then you measure the frequency to land in a certain region of the phase space. And this then will be given precisely by the measure. If I put a characteristic function in a subset, you get precisely the measure in the subset. You can actually measure experimentally this measure if you believe that the system is ergodic. But more often than not, this is actually just an assumption, a model, rather than mathematically proven. Okay, and so here's an example. For instance, P is ergodic with a shift, and then the chance to visit the cylinder set is precisely the measure of the cylinder set. So this information that I said that we actually, in the beginning, we were constructing a measure here by already knowing what the chance was to arrive somewhere. But in the end, somehow, you'll see that actually there's a mathematical description for it. Okay, so if you have ergodicity, you can do this. And let's measure this now. What is the chance to end up in the subset A of 0, 1 for an orbit of our system? Well, I can, of course, also kind of take the. No, I don't care what time we arrive, so I just take the. I take the thing here, I take the screw product system, because I'm interested. So I'm going basically into the screw product picture. There I know that I have ergodic invariant measure, which is mu. But what is now this thing? This is the integral both over the space and also over sigma 2. But the integral over sigma 2 gives me precisely this marginal. So I get the marginal of this measure of A. Just by that ergodic theorem. And the marginal of this measure was precisely my stationary measure by definition. So I see that the chance to arrive in set A, the frequency, the relative frequency, is precisely the measure of a stationary measure, which in our case was also the fixed point of, unique fixed point of my Markov process, my Markov operator for the measures. So you see here that the ergodic theorem relates those things in a very natural way. And it's essential for this, otherwise, because if I just have an invariant measure, it's just a game. I have some measure and it pushed forward by something, but what does it tell me about anything? Not clear. But only through the ergodic theorem we say that it means something. Because I can put other functions here and I get expectation of other functions. This is the characteristic function. Good. And so I can, of course, do this also for any other observable. So I get this formula. And also I get here basically the stationary measure appearing. So the stationary measure is not ergodic because there's no dynamics in it. Stationary measure is just a fixed point of the fixed point of the Markov operator. It's also the marginal of the invariant measure. But this is the guy that appears in the ergodic theorem. And sometimes Markov process also called ergodic, precisely if the underlying system somehow is ergodic, and when this kind of relationship holds. But one has to be a little bit careful because the invariant, this stationary measure is not invariant on the dynamics. If I take the stationary measure and I push it with one realization of the dynamics, we know what happens to the pullback, it converts to 1 point. The stationary measure is not invariant on the dynamics, it's actually invariant on the dynamics on average over all realizations of the noise. So you have no dynamic information whatsoever. So here's a can. So it's interesting to know that if all, because all trajectories convert exponentially to slope. So here we have, sorry, so we have mu almost surely. What's mu? Mu has a component in p and a component in this direction. But the nice thing is, because we know that all points converge, we can actually get a slightly stronger ergodic theorem here on the dynamic, because we have random fixed point, is that you can get p almost surely just on the noise. We don't care about initial condition, because in some sense all initial conditions exponentially converge. But we need to give in a little bit with observable. We rather have continuous, because we want some kind of convergence of behavior. So instead of just integrable function, if I have a continuous observable, in this setting, with a random fixed point in the background, I can get a stronger ergodic theorem, because I get one that actually doesn't depend anymore on initial conditions. Good. So there's also alternative measure, which is also invariant. So rho cross p, it's just like the stationary measure cross p that has a huge support, just south and south, and this could be or could be not be ergodic. In our case, it was ergodic. And then, of course, I get also the same theorem, but then I get rho cross p almost surely. And you see that how, in some sense, when we now have some information about the dynamics, I can somehow get rid of rho. So that means so usually this is some a technical thing. So if you think of the Markov process and you assume some underlying ergodicity, you will basically immediately get something like this, presuming ergodicity in the background. But if you know that we have a random fixed point in the background, then somehow we can actually say for all initial conditions with a mild condition. Okay, so that's something I think that's a nice example here, where we see that some dynamical information somehow adds something on some topic which is basically very classical statistics. So ergodic Markov processes, ergodicity, Bldg theorem is things that one usually like to kind of assume or use, and you get some kind of by some more information about the dynamics, you get really a tangible strengthening of the result. Okay, so of course we can do generalize these things in more general. We can actually take general iterative function system with many more contractions in much higher dimension. I can and then I can apply in a random fashion contractions in a high dimensional space. So what I did just on the line with two contractions, this is the very simplest example. I can make it much more complicated, but in fact everything I did will still hold. So the ergodic, ergodic theory and stationary measure, the Bldg averages, and this is a kind of it was an important result by John Elton. John Elton has this result precisely kind of this result that we just kind of obtained basically for all x and p almost surely ergodic theorem for continuous function. And that was used for these iterative function systems. So in general, and as I said, the direct proof that you can do, and maybe that's also a possible exercise somehow, is to show that if you know about a random fixed point, that you can prove that you can actually reprove Elton's theorem, which actually Elton doesn't really use that directly at all. He doesn't really use the point of view, and maybe it's more cumbersome. So I'd like to say a little bit more to finalize the talk about this application of iterative function systems, because maybe it looks like kind of silly thing to do to look at iterative function systems, but actually it was a big deal. So here you have a picture, and it's also on the poster, and this is so-called Barnsley Fern, and so this is actually the image of an orbit of random dynamical system generated by three contractions on the plane. So we have three affine contractions, and if I just take one initial condition and I just run it forward, lo and behold, this picture emerges. And it looks kind of appealing. So one of the nice things is that actually it's a itself similar. So this leaf is similar to the whole leaf, etc., etc. So there's a very nice self-similar structure to it. So what are the contractions that you can use to make this up? It's in this picture. So you start with the black square, and I've taken a affine transformation, just affine, so it's linear plus translation. You take this black square into the purple square, this purple square into the blue square. Only 3 transformations. So this is like my T0, T1, but now I have T0, T1, T2, 3 transformations. And now what I do is I take an initial condition, and I run this, and I take randomly, say, chance 1 third for each, and just run it forward, and I get such a picture. So what's the picture that we look at? What is this picture? The picture is stationary measure. Because what is the picture? The picture has an intensity. You see more color if there's more dots on one place. Let's assume that we have infinitely high resolution, or high enough resolution not to get 2 points on the same dot. So we get more color, where it's more points. So it measures the frequency where we are. By the Kyoto theorem, we know that the frequency is a measure of the invariant measure of the stationary measure. So what we here see is the picture of the stationary measure. And in fact, we see also the support of the stationary measure. The support of the stationary measure is a fractal, just like the Cantor set, but then a little bit more complicated. Okay, so what's the interest in this? Well, the interest is that maybe we can actually. So this is a picture that looks appealing. It looks like of everyday life, and I tell you this is actually an object which is mathematically generated. And I can ask a question, say, how many pictures can I generate with such a procedure? Is there any limit to what I can do? So this is a fractal, it's a kind of fractal image, and looks like a leaf. So it could be that maybe it was a real leaf that looked like this. So the question, like, could I find the inverse? Could I make a program where I take a leaf and I say, does it look like a fractal? Which fractal? And can I actually generate it with such an iterative function system? Okay? And so this is the topic of this book. It's a well-known book, 1988. Michael Barnes, big fractals everywhere. And basically, the gist of the story, you see some picture of, I think it's sunflowers from Hall, is that, yes, that in some sense you can. So in some sense you can approximate any image by a fractal, and by such a fractal that I can then approximate it in terms of the density of a random dynamical system. And so what's the idea? I have a picture, this painting, and I like to encode it. I like to store it somewhere. Now, maybe you say, lots of information in this picture, so how much space do I need for this? Or maybe the further the better. I want the space to save this picture. There's a lot of detail in this picture. Maybe a lot of memory. But 3 affine transformations is very little memory, just some computational power to generate this picture, but not that much. So the question is, can I do the inverse transformation? Can I go from pictures to transformations and then store everything in those transformations? So, okay, what is the presumption? Yeah, of course, that we have basically that storage power is very expensive, and that computational effort is very cheap. That's a good economic model. That means that we don't have to store much, we store less, but we maybe have to compute a lot. And so to compute from the transformation in this picture is very quick. To find the transformations is much more difficult. So let me say something about that problem. It's so-called well-celebrated Poincaré theorem of Barnsley. And it says that if I have some complementary space, some set of contractions with a uniform bound. So we have some uniform. We know that everything really contracts at least with a certain rate. And let E be an associated attractor for this irregular function system. So this is actually for this map T that I had before. And this is also just the set-wise one. This kind of thing, so I just map the sets forward. And if I can approximate these things in the Hausdorff distance, So like, well, if I have an object h of x, and if m of f is precisely, so f is just some set. Yeah, and if f is invariant under this operator, that is a fixed point, and we have a unique proof, but then I can do the following thing, then the difference in Hausdorff between f and m of f.
Sorry, f is not invariant.
No, so not invariant, sorry, this is sorry, yeah, image. E will be the invariant one. So the Hausdorff distance between E and f is smaller or equal than the Hausdorff distance between f and m of f. So this is my target picture. This is my approximation by the so ideally what I would like is that f and m of f are equal. So I take a picture, which is f, and I try to find transformations t so that m of f is very close to f. I do this with contractions with a certain rate, which comes into this estimate. So if this is very small, and this is kind of around given, then I have a bound on the difference between my picture that I want to approximate and the attractor for the iterated function. E is the attractor. So the idea is the following. So if I can find a very good overlap between f and mf, then I can actually generate the set E by just a repeated iteration of f. This is the idea. So is it looks like, so this collage scheme, what's a collage? Because I have a set f. And I try to kind of find transformations so that I can shrink the picture and map it back onto itself so that it covers very nicely. So in the example of the fern, this was exactly possible. Look, I have the whole picture, yeah, and then I shrink it, 1, 2, 3 shrink copies, and I put it exactly on the picture. Now, if it's exact, then this term is 0, and I get an exact result. Now, you shouldn't maybe expect that you typically can do it exactly, but maybe you can do it approximately. And maybe some pictures are better for that than others. Okay, so how do you prove that? Well, you just basically write out these things, and you use basically the triangular inequality many times. So you write the difference, you write the difference as the sum of difference between ni by iterates. Ni by iterates has a Lipschitz estimate, comes with S. So I get the thing, and you get the sum over S, which gives you a geometric series 1 over 1 minus S. Which M goes to infinity. Yeah? So there's a limit, and goes infinity in this as well. That's actually a very elementary argument. That's very powerful, and there's also a version with probabilities. So I can now do it for the measures. I also know that I can do it with the Markov operator, and I can do this on the measure space with the Hutchinson metric, and lo and behold, it's exactly the same trick. I can find something where the measures are roughly similar. If the measures are similar, then I can actually generate the things by the measure is well approximated by the stationary measure. And how do